My name is Andrew Coble, and this is my Project 5 presentation for CE 570. For this project, we were tasked with defining a vector field on a 3D body, which can be seen in the top left. Then we were tasked with calculating the divergence of said vector field, which can be seen below it. Finally, we were tasked with verifying the left-hand side and the right-hand side of the divergence theorem, which have to match, which will be done shortly. Also seen in this slide is the divergence of the vector field and the vector field within my MATLAB code. The scalar field in this case is just the divergence of my vector field. Here is the MATLAB parameterization of the hemispherical portion of my snow cone. Most of the code has been carried out from previous weeks, but the updated portion is the scalar field and the vector field functions. You can see that the vector field has a respective x1, x2, and x3 values plugged in from the hemispheric parameterization. I also added a snapshot of my vector and scalar field in the right-hand corner just to help show how the functions have changed. In this slide, the parameterization of the cylinder and cone portion of my body is shown. New pieces to the code include the scalar field and vector field functions like the last slide. You can see for both cases I have plugged in the respective x1, x2, and x3 values into the scalar and vector field functions. This slide displays my graphical outputs of my MATLAB code. Starting on the far left-hand side is the plot parameterization of my snow cone. Following that is a scalar field plot, which again is just the divergence of v. I also added my scalar field at the bottom of the image for reference. On the far right is the plot of my vector field. As you can see, the farther you work your way up the snow cone, the larger in magnitude the vectors are, simulating the displacement of my cone at the top. Moving on, I would like to verify my hand calculations on the left-hand side of the divergence integral. I started by verifying the volume Jacobian of the hemispherical body. Next, I added that to the divergence theorem expression and plugged in the required x2 value, which was r cosine phi. Then I triple integrated over r, phi, and theta to obtain a final value of negative 85.7864. The verification of the left-hand side of my divergence theorem for my cylindrical portion of my body. As you can see, I first derived the volume Jacobian, which is just equal to r. I then added in the x2 portion of my code, which is r sine theta. Next, I added it to the divergence theorem expression and triple integrated over r, theta, and z to obtain a value of negative 32.17. Here is the divergence verification of the third and final portion of my body, the upright cone. I began by deriving the volume Jacobian, which resulted in z over 9h squared times r. Then I plugged in the respective x2 value, which is r times z times sine theta. Then I plugged all these values into the divergence theorem, and then I triple integrated over r, theta, and z, which resulted in a value of negative 54.2867. Next, I quickly derived the right-hand side of the divergence theorem for the hemisphere, cone, and cylinder. First off, you can see the hemisphere, then the cylinder, and then the derivation of the upright cone. Finally, I threw all these values into MATLAB and computed a value of negative 172.2431. Finally, I added up the values on the left-hand side of the divergence theorem, which was negative 85.7864 minus 32.17 minus 54.2867, which obtained a value of negative 172.2431, which matches both the right-hand side of the divergence theorem and then also the value obtained from my MATLAB code. Thank you for watching.